Let us begin gently with you falling. Not tonight and not really. You are perfectly safe where you are, and the nearest black hole is thousands of light years away and has no interest in you whatsoever. But as a thought, as a quiet exercise for a sleepy mind, let us find out what would actually happen to a person who fell into one. It is one of the most asked questions in all of science, and the answer is far stranger, and in some ways far gentler than most people expect. You would not be pulled apart in a screaming vortex. You would not, in the way films suggest, be sucked in from a great distance. And depending on which black hole you chose, you might cross the point of no return without noticing anything at all, and go on quite comfortably for some minutes afterward, with the whole universe still visible above you. And then physics would run out of things to say. Tonight we are going to take that fall slowly all the way in and see exactly what happens at each stage and why. And I promise to bring you back out again at the end, safely, into your own warm bed, which is where you will remain throughout. But before we go a step further, let me ask you something, softly, because it matters more than you might think. If these quiet journeys through the strange corners of our universe help you set down the weight of your day and find your way toward rest, then please, take just a moment right now before you settle any deeper into the warm and subscribe. It is one small tap. But it means the next of these will find its way back to you on some future restless night when sleep is a long way off and you need somewhere gentle to put your mind. And it helps, more than you could possibly know, to keep these stories being made for you and for everybody else out there in the dark tonight looking for a little peace. So if you would, subscribe and stay with me night after night as we wander together through the great slow mysteries of the universe. And tell me, if you will, from wherever you happen to be resting tonight, in whatever quiet corner of the world is holding you. Where are you listening from? And what hour has it reached where you are? Leave it in the comments below. It is a lovely thing to see all the places and all the hours gathered there together, all of us drifting off beneath the same turning sky, in 100 different countries and 100 different hours, all of us here in the dark at once. And now, let your shoulders come down, and let your breathing slow, and let the whole weight of your day loosen and fall away. Come with me out into the dark, a very long way from here, and let us go and look at something we will never have to visit. Let us begin with what a black hole actually is, because almost everything most people believe about them is wrong, and the corrections make everything that follows much easier to picture. The first correction is the most important, and it is this. A black hole is not a vacuum cleaner. There is a persistent idea that black holes suck things in, that they exert some special pull that reaches out and drags in everything nearby. They do not. A black hole's gravity behaves exactly like the gravity of anything else with the same mass. Here is the way to feel this. Suppose our sun right now were instantly replaced by a black hole of exactly the same mass. What would happen to the Earth's orbit? Nothing. Nothing at all. The Earth would continue in precisely the same orbit, at precisely the same distance, at precisely the same speed, for as long as it likes. It would get extremely cold and dark, which we will come to on another night, but gravitationally nothing would change. From 150 million kilometers away, a black hole of one solar mass and a star of one solar mass pull identically, because gravity depends on mass and distance and nothing else. So a black hole is not dangerous because of some special reaching power. It is dangerous for one reason only, which is that all of its mass is packed into an extremely small space, and that means you can get very, very close to all of it at once. With an ordinary star, you cannot approach the center because the surface is in the way. Long before you get near the middle, you hit the outside. With a black hole, there is no surface to stop you. You can keep falling inward, closer and closer to all of that mass, and gravity climbs and climbs, and there is nothing to hit. That is the whole of it. Not a special force, simply the ability to get close. The second thing to understand is the event horizon, and the name is very good and the popular picture of it is very bad. The event horizon is not a surface. It is not a wall or a membrane or a shell of anything. There is nothing there. If you were falling in, you would not see it and you would not feel it, and there would be no bump, no shimmer, no boundary of any kind to mark it. It is a purely mathematical boundary, defined by a single property. Inside it, every possible path leads inward. Outside it, escape is still possible. And that phrase, every possible path leads inward, is the key to this entire evening, and it is worth taking slowly. Ordinarily, when we say a place has strong gravity, we mean escape is difficult. You need to travel fast. On the Earth, you need to reach about 11 kilometers a second to leave and never come back. On a more massive world, you would need to go faster. That is a matter of difficulty. Inside a black hole's horizon, it is not a matter of difficulty. It is that outward has stopped being a direction you can travel in. Space is curved so severely in there that all the paths that used to lead away have been bent around to point inward. Not most of them, all of them. It does not matter which way you steer, or how powerful your engine is, or how fast you go. Every direction leads deeper in the same way that every direction leads into tomorrow. That is the best comparison I know for it. Inside a black hole, moving away from the center becomes exactly as impossible as traveling backward in time. It is not that you lack the power. It is that the destination is no longer on the map. Rest a moment there and let that settle, because once you have it, everything strange about the rest of tonight makes sense. Now, before we jump, there is one crucial decision to make, and it turns out to matter enormously. Which black hole are you falling into? Because they come in very different sizes, and the experience is completely different depending on which one you choose. This surprises people who tend to assume that a bigger one would be more violent. The opposite is true, and the reason is one of the loveliest counterintuitive facts in physics. Let us take the small one first. A black hole formed from a collapsed star might have a mass of 10 times our Sun, packed into a sphere about 60 kilometers across. The horizon of such an object is roughly the size of a small city. Now, gravity gets stronger as you get closer. That is ordinary. But the important thing when you are falling is not the strength of gravity. It is the difference in strength between one part of you and another. Suppose you fall feet first. Your feet are closer to the center than your head, so gravity pulls harder on your feet than on your head. On the Earth, that difference exists, but it is unimaginably tiny, and you never notice it. Near a small black hole, that difference becomes enormous. Because the object is so small, the gravity climbs so steeply that even across the length of a human body, the difference is catastrophic. Your feet would be pulled far harder than your head, and you would be stretched. It would begin gently and become extreme with terrible speed, because these forces rise very sharply as you approach. First, a sensation of being drawn out, then a strain, then a pull no material can withstand. First on the body, then on bone, then on the very molecules, and everything is drawn out into a long, thin stream of matter falling inward. Physicists gave this a name in a rare fit of whimsy, and the name is spaghettification. It is one of the very few pieces of formal scientific vocabulary that sounds like a joke and is not. And it is worth being precise about what is happening, because the usual description undersells how strange it is. You are not being crushed. That is the instinctive picture, and it is wrong. You are being stretched, lengthwise, along the direction of the fall. And at the same time, you are being squeezed sideways. Because gravity pulls toward a single point, and your left shoulder and your right shoulder are both being pulled toward that same point, which means they are being pulled very slightly toward each other. So you are drawn out long and thin in one direction and pinched narrow in the other two, like a piece of dough being rolled. The effect has been observed, incidentally, though thankfully not on anybody. Astronomers have watched entire stars get too close to black holes and be torn apart in exactly this way. The star is stretched into a long stream of glowing gas, part of which is flung away and part of which spirals in and heats up and blazes, producing a flare of light that can be seen across the universe and that fades over months. These events have a name in the literature, and it is a fine one. Tidal disruption events. A whole star drawn out like taffy over a period of days. So the process is real, and it has been seen, and it is quite thoroughly documented. It simply has never happened to a person, and never will. And here is the crucial point about a small black hole. This happens well outside the horizon, thousands of kilometers out. Long before you reach the point of no return, you would already have been drawn out into a thread. So for a stellar mass black hole, the answer to tonight's question is short and rather anticlimactic. You would be torn apart by tidal forces long before anything interesting happened, and there would be no crossing of any boundary and nothing to see. Which is why for the rest of tonight we are going to choose a much larger one, because here is the counterintuitive part. The bigger a black hole is, the gentler the fall. At the horizon of a truly enormous black hole, one of the supermassive ones that sit at the centers of galaxies, with a mass of millions or billions of suns, the tidal difference across a human body is negligible. You would feel nothing at all. The reason is geometry. A bigger black hole has a much larger horizon, so the horizon sits much further from the center, and gravity does not have to rise nearly as steeply to reach the critical condition. The curvature at the boundary is gentle, spread out over an enormous scale. Think of standing on a small ball versus standing on a very large one. On a small ball, the surface curves away sharply under your feet. On a very large one, it feels flat. Same principle. Bigger means gentler, locally, so we will fall into one of the great ones. The one at the center of our own galaxy has about 4 million times the mass of the Sun, and its horizon is roughly 24 million kilometers across, which is a bit bigger than the orbit of our innermost planet. Something to fall into with a bit of room, and it is worth pausing on that scale for a moment, because black holes come in sizes that are hard to hold in one's head at the same time. The small ones, formed from collapsed stars, are city-sized, 10 times the mass of the Sun compressed into something you could drive across in an hour, if driving across such a thing were possible. The great ones at the centers of galaxies are of an entirely different order. Millions of times the Sun's mass, billions, for the largest. The biggest known have horizons larger than our entire solar system, so vast that light, which crosses from the Sun to the Earth in 8 minutes, would need more than a day simply to travel across one. And a strange consequence of that size is that the largest black holes are not dense at all, in the everyday sense. This surprises people, because density is the whole story with the small ones, but the horizon of a black hole grows in direct proportion to its mass, while the volume it encloses grows as the cube of that. So the bigger they get, the less dense they are, on average, inside the horizon. Get one large enough, and the average density inside the horizon drops below the density of water. Larger still, and it drops below the density of air. There are calculations suggesting that a black hole with the mass of a large galaxy cluster would have an average density comparable to a decent laboratory vacuum. You could, in principle, be inside a boundary of that kind and be floating in what appeared to be near empty space, with no sense of density or compression whatsoever, and still be unable to leave. The mass is not spread out, of course. It is concentrated somewhere far below. But averaged over the enormous volume enclosed, the number is tiny. That is one of the odder facts in this subject, and it makes the point that a black hole is not really an object in the way a rock is. It is a region of space with a particular property, and the property is about where the paths lead. And now let us jump. You are floating some distance out. You are in a spacesuit, and let us give you a large window, and a clock, and a colleague who has kindly agreed to stay behind at a safe distance and watch, and to whom you can send radio messages. We will need her later. You release your hold and begin to fall. Now, before we go on, we should quietly deal with something that would in practice kill you long before any of the interesting physics arrived, and which almost every account leaves out. Most real black holes are not clean. They are usually feeding. Gas from the surrounding region falls toward them, and because everything is in orbit and nothing falls straight in, that gas forms a vast flattened disk, spiraling inward, getting faster and hotter as it goes. Friction heats it to millions of degrees. It blazes in ultraviolet and X-rays. The inner regions of such a disk are among the most violent environments in the universe. Anything falling through that would be cooked long before it reached the horizon, not stretched, simply irradiated thoroughly by a furnace brighter than most galaxies. There are also magnetic fields wound up into enormous structures and jets of material blasted out from the poles at nearly the speed of light, extending for thousands of light years. So for tonight, we are going to pick a quiet one, a black hole that has already eaten everything nearby and is sitting starved and dark, with nothing falling in and no disk at all. These exist, and in fact most black holes spend most of their lives in exactly that state, since the feeding periods are relatively brief. The one at the center of our own galaxy is currently very quiet indeed by the standards of these things. So, a starved black hole. No disk, no jets, no radiation. Just the dark, and you, and the fall. The first thing to say is that falling is comfortable. You are weightless because falling freely always feels weightless. You feel nothing pulling on you. There is no wind, no sound, no sensation of speed at all except what you can see. It is exactly like floating, because it is floating all the way down. Ahead of you is the darkness, and it is worth being precise about what you see, because the popular image of a black hole is far more dramatic than the reality would be from close up. If your black hole is quietly starved, with no gas falling into it, there is no glowing disk, no fire, no light. There is simply a circle of absolute black, growing steadily larger as you approach, blotting out the stars behind it. And around the edge of that black circle, something extraordinary is happening to the light. The intense curvature bends the paths of light rays around the hole, which means you can see stars that are actually behind it, their light curved around the edges and brought to your eye. The sky appears distorted around the black circle, smeared and doubled and stretched into arcs, with a bright thin ring of concentrated light right at the boundary. As you fall closer, that distortion grows, the black circle swells, and the entire universe behind you begins to gather itself into a shrinking region above you. This is one of the strangest visual effects of the whole journey. As you fall, the incoming light from everything outside becomes concentrated into an increasingly narrow cone. The entire sky, everything that exists, every star and galaxy, all of it, is squeezed into a smaller and smaller bright circle overhead, while the black takes up more and more of everything else. Rest a moment on that image because it is quite beautiful and nobody has ever seen it. Below you, an expanding blackness that fills the world. Above you, the entire universe compressed into a brilliant circle, growing smaller, ringed with distorted light. And the colors shift as well. Light falling in with you gets shifted toward the blue, so the universe overhead brightens and blues as you go, growing more intense. There is one more feature worth mentioning because it is quite peculiar and it lies outside the horizon, so you would pass through it on the way. At a certain distance above the horizon, there is a place where light itself can orbit, where the curvature is exactly right that a ray of light traveling sideways will follow a circular path around the black hole and come back to where it started. It is called the photon sphere, and it is a real location at 1.5 times the radius of the horizon, and it means something quite strange. If you were somehow able to hover exactly there, looking sideways in the direction of the orbit, you would see the back of your own head. Light leaving the back of your head would travel all the way around the black hole and come back to your eyes from the front. You would be looking at yourself from behind, in real time with the whole black hole in between. You could not actually hover there, because staying in place that close would require impossible thrust. But the geometry is real. There is a shell around every black hole where light goes in circles, and any light that strays into it too precisely will simply orbit until something disturbs it. That thin, bright ring in the images we have taken of black holes, the glowing circle around the shadow, is closely related to this. It is light that has been bent right around, sometimes more than once, and concentrated into a narrow band. When you look at a photograph of a black hole, part of what you are seeing on the near side is light from the far side, brought around the back and delivered to your eye. Now, while you are falling, let us go and check on your colleague, because what she is watching is completely different, and this is the part that people find hardest. She sees you falling away from her, and she sees you slowing down. Not because you are slowing. From your point of view, you are accelerating steadily. But near a black hole, time itself runs at different rates, and the deeper into the gravity you go, the slower your clock runs as measured by someone far away. So from her position, your clock is dragging, your movements grow sluggish, your radio signals arrive stretched, the pitch dropping, the gaps between words growing longer. Your image reddens because the light leaving you is climbing out of a deep gravitational well and losing energy in the process. And as you approach the horizon, from her point of view, you slow almost to a stop. She never sees you cross. That is the key thing. From outside, You appear to hang there, just above the boundary, redder and redder, dimmer and dimmer. Your final moment stretched out toward eternity. Your last signal drawn out so long that it fades below anything detectable. You do not vanish suddenly. You fade. Within a small fraction of a second of real time, the light from you becomes too dim and too stretched to detect, and you are simply gone, frozen at the edge forever as far as she is concerned. And there is a small poignancy in that which is worth a moment. This is why black holes were briefly called frozen stars before the better name arrived, because from outside nothing ever finishes falling in. Every star that ever collapsed, every cloud of gas, every unfortunate object that ever crossed a horizon is still there in a sense from our point of view, frozen at the boundary, its final instant stretched out toward eternity, its light drained away to nothing. There is a whole history of things arriving, permanently unfinished, on the outside of every black hole in the universe. That is not a poetic image. It is what the mathematics says an outside observer would compute. And yet every single one of them, in its own reckoning, went straight through without pausing and reached the end within seconds. Meanwhile, in your suit, none of this is happening. You have not slowed down at all. Your clock ticks normally. Your thoughts run at their usual pace. You are falling faster and faster, and you sail across the horizon without any sensation whatsoever. And this is the point that trips almost everybody, so let me put it plainly. Both accounts are correct. There is no fact of the matter about who is right. Time is not a universal thing ticking away everywhere at once. It is local. Her clock and your clock both tell the truth about their own positions. You crossed. She saw you hang there forever. Both are true, and there is no contradiction, because there is no single universal now for the two of you to disagree about. Rest a moment there, and let that be strange rather than troubling. This is not a trick or a paradox. It is simply what living in curved space-time is like. And we have measured smaller versions of the same effect with clocks on aircraft and satellites, and it is correct. Now, there is a related idea that comes up constantly and is worth clearing away, because it is very widespread and it is wrong. You have probably heard that if you fell into a black hole, you would see the entire future history of the universe play out above you at high speed as time outside raced forward. It is a wonderful idea, and it is not right. You do not. The reasoning behind the myth is understandable. If time outside runs fast relative to you, then surely you would see everything sped up. But the actual calculation of what an infalling observer sees is more subtle, because you are also moving rapidly away from that incoming light, and the two effects largely cancel. What you actually see as you cross the horizon is roughly the outside universe as it is at that moment, somewhat distorted and brightened, not an accelerated film of all future history, and you certainly do not see the end of the universe. If you did, that would be a way of getting information from arbitrarily far in the future, and the mathematics does not permit it. So the sky above you is compressed and bright and distorted, but it is not fast-forwarding. It is more or less the ordinary universe, seen through a very strange lens. And now you cross. There is nothing to feel. No jolt, no membrane, no change of any kind. You would not know it had happened. If you had a very good map and a very good clock, you could calculate that you had passed the boundary, but there is no local experiment you could perform that would tell you. The place where you cross looks exactly like the place 100 kilometers above it. That is worth pausing on, because it is the single most counterintuitive fact about black holes. The point of no return is not a place. There is nothing there. You pass through empty space feeling nothing, and the only thing that has changed is which futures are available to you. Before, you could still leave. After, you cannot. And nothing marked the transition. Now let us talk about what you can and cannot see from inside, because this is often misunderstood too. You can still see out. The sky is still there above you, that bright, compressed circle. Light from outside can still fall in and reach you, because falling in is the one thing everything can still do. What cannot happen is the reverse. Nothing you emit will ever get out. You can watch, but you cannot be watched. Your radio messages to your colleagues stop arriving, not because you have stopped sending, because the signals, like everything else, now have only inward paths available. And here is a detail I find quietly haunting. If a second person jumped in a minute after you, they would be inside with you, and you could in principle see them, because their light can fall inward toward you. Two people inside a black hole are not isolated from each other. They simply cannot tell anyone outside about it. Now, how long do you have? This is one of the most surprising numbers in all of this, and it is much shorter than people expect. Once inside, everything falls toward the center, and there is a maximum possible time you can survive between the horizon and the end, no matter what you do. And it depends only on the mass of the black hole. For the one at the center of our galaxy, 4 million solar masses, it is somewhere in the region of half a minute. Half a minute. From crossing the boundary to reaching the center. So about 30 seconds of your own time, and there is nothing whatsoever you can do to extend it. And here is a beautifully strange detail. Firing your rocket engines to try to escape makes it worse. Because inside the horizon, the center is not a place in space that you are falling toward. It is a moment in time that you are falling toward, and accelerating in any direction in this geometry brings that moment sooner, exactly as vigorous activity does not let you avoid tomorrow, but does tend to use it up faster. The longest possible survival is achieved by doing absolutely nothing, simply falling freely without struggling. Rest a moment there, because that is such an odd and almost gentle instruction. Inside a black hole, the only way to have the most time is to stop fighting and drift. And there is a related oddity worth mentioning, because it is one of the strangest things in the whole subject. Inside the horizon, space and time swap roles. Outside, you can move freely in space and are carried inevitably forward in time. You can go left or right or up or down as you please, but you cannot choose to go to yesterday. Time carries you along in one direction, whether you like it or not. Inside, that is inverted. The radial direction, in toward the center, acquires the character that time has out here. It becomes the thing you are carried along inevitably, with no choice about the direction. That is the precise mathematical reason why you cannot escape. Not because gravity is strong, because getting further from the center has become as impossible as getting to yesterday. The center is not somewhere in front of you. It is a moment in your future, and it is coming, exactly as tomorrow morning is coming for you now. That is also why the phrase point of no return, though not wrong, undersells it slightly. The horizon is not the point past which returning is very hard. It is the point past which returning has stopped being a kind of thing that exists. For a truly enormous black hole, one of the largest known, with billions of solar masses, the time from the horizon to the center can be a matter of hours rather than seconds. So in principle, you could cross the boundary of one of the giants, feel nothing at all, and then spend a leisurely afternoon inside, floating comfortably, watching the compressed universe above you, entirely unable to leave and in no immediate distress. That is a strange thing to picture. Somebody sitting quietly in a spacesuit, perfectly comfortable, watching the stars, several hours from the end and completely unable to do anything about it, in a place from which no news will ever emerge. But eventually, whichever one you chose, the tidal forces catch up with you. Because as you approach the center, you are approaching all that mass concentrated in a vanishingly small region, and the gentleness of the giant horizon is a purely local effect that does not survive the approach. The stretching begins and it grows, and this time there is no escaping it. And the spaghettification we described at the start happens after all, at the end rather than the beginning. And then you reach the center. And here, honestly, our physics stops. The mathematics of the theory says that all the matter is crushed into a point of zero size and infinite density, and that the curvature of space and time becomes infinite there. Physicists call it a singularity. But I want to be honest about what that word means, because it is often presented as a discovery, and it is really an admission. Infinity is not an answer in physics. When infinity appears in your equations, it almost always means that you have pushed a theory beyond the range where it applies, and it is telling you politely that you need a better one. We have two great theories. One describes gravity and the shape of space at large scales, and it is superb. The other describes matter and energy at the smallest scales, and it is also superb. They have never been successfully joined, and they contradict each other. Nearly everywhere in the universe that does not matter, because gravity is negligible where things are tiny and things are enormous, where gravity is strong. The center of a black hole is the one place where both are true at once. Enormous mass, vanishing volume. Both theories are required and they disagree, and nobody has resolved it in a century of trying. So the honest answer to what happens at the very end of your fall is that nobody knows. Not in a mystical sense, in the plain sense that the necessary physics has not been worked out yet. There may be no point of infinite density at all. There may be something else entirely, some structure that only a completed theory would reveal. The question has been open for 100 years. Somebody will answer it. Possibly somebody alive tonight. Rest a moment there, and let that be a comfort rather than a frustration. The universe still has a sealed room in it. There is one place where our best knowledge simply runs out, and it is sealed behind a boundary that no message can cross, which is either a wonderful piece of cosmic tact or a very frustrating one, depending on your temperament. Now, before we finish, there is one more question hanging over all of this, and it is the deepest one in the subject, and I would like to leave you with it, because it is a truly open puzzle and rather beautiful. What happens to the information? Here is the problem. In physics, information is not supposed to be destructible. The details of a thing, the arrangement of its parts, are in principle always preserved. Burn a book, and the information about what was written is scrambled beyond any practical hope of recovery, but in principle it is still there, encoded in the smoke and the ash and the light, and a sufficiently godlike accountant could reconstruct it. That principle is deeply woven into physics, and black holes appear to violate it, because black holes evaporate. This was worked out 50 years ago, and it says that black holes give off a very faint glow, and over unimaginable spans of time they shrink and eventually disappear entirely. But the radiation they give off appears to carry no information about what fell in. It seems to depend only on the mass and spin of the hole, not on whether you fed it a library or a lump of lead. So if a black hole swallows something and then evaporates completely, where did the information go? It cannot be inside, because there is no inside anymore. It does not appear to be in the radiation. It seems to have simply ceased to exist, which physics says should be impossible. This is the information paradox, and it has occupied some of the finest minds alive for 50 years, and there is now a broad expectation that the information does come out somehow, encoded in the escaping glow in some subtle way, though exactly how is still argued about. It has produced some remarkable ideas along the way. One of them proposes that everything that falls in is somehow also recorded on the surface of the horizon, so that the interior of a black hole is, in a sense, a projection of information stored on its boundary. That idea has been taken seriously enough that some physicists suspect it may be true of the universe as a whole, that the three-dimensional world we live in might be describable entirely in terms of information on a distant boundary. Another line of thought led to a rather alarming suggestion. If information must be preserved, then some of the assumptions in our gentle picture of the fall may be wrong, and there might be something violent waiting at the horizon after all, a wall of enormously energetic particles that would destroy anything crossing it instantly. That idea is not mainstream, and most physicists dislike it because it contradicts the principle that there should be nothing locally remarkable about the horizon. But nobody has been able to rule it out cleanly, and the fact that it will not go away is a good sign that something in our understanding is still missing. I mention all of this not to unsettle the peaceful fall we just took, but because it shows what these questions are actually for. Nobody cares about black holes because they are dramatic. They are studied because they are the one place where all of our physics is forced into the same room at the same time, and made to give a consistent answer, and so far it cannot. I mention it because it is a lovely example of something worth carrying to sleep with you. The deepest problems in physics are often not about faraway exotic things at all. They are about whether the universe is allowed to forget. And now let us bring you back. You are not falling. You never were. You are lying in a warm bed on a solid world, with a floor beneath you that has held perfectly steady your entire life and shows no sign of stopping. The nearest black hole to us is something like 1,500 light years away. That distance is difficult to convey, so let me put it this way. If you set out tonight in the fastest spacecraft humanity has ever built and traveled without stopping, You would not arrive for over 20 million years. They do not wander. They do not approach. They sit in their orbits around the center of the galaxy, exactly as the stars do, moving no faster and no more purposefully than anything else, entirely indifferent to us. Nothing you have heard tonight is a thing that will ever happen to anyone. It is a thought experiment. That is all it has ever been. But it is a thought experiment that has taught us an enormous amount, because working out what would happen to a falling person is one of the ways physicists actually probe the structure of space and time. That imaginary faller has done more for our understanding of gravity than almost any real observation. So somebody in a chair with a pencil, imagining a fall that will never happen, gently pushed forward the understanding of the universe. That is what we have really been doing tonight. And I think that is the nicest thing to take from all of this. If you take anything at all, not the darkness and not the danger, neither of which has anything to do with you, but the fact that a person can sit quietly in a room with no equipment at all, and by carefully imagining a situation that could never occur, work out something true about the structure of reality. Every strange thing we have talked about tonight, the compressed sky, the frozen image at the boundary, the 30 seconds, the swapping of space and time, all of it came out of pencil and paper and patience. Nobody has been. Nobody will go. And we know all of this anyway. That is a remarkable ability for a species to have, and it belongs to you as much as to anyone. You have been doing it yourself for the last hour, lying still in the dark, falling into something 1,000 light years away without moving an inch. And so let it rest now. Let the black circle grow soft and dim and very far away. Let the compressed sky and the bending starlight and the 30 seconds and the sealed unanswered question all drift off into the enormous distance where they belong, thousands of light years from this room, where they have been sitting quietly for billions of years, and where they will remain undisturbed long after tonight. There is nothing there that concerns you. There never was. It is simply a strange and interesting feature of a very large universe, most of which is empty, and almost all of which is extremely far away. You are here instead, which is the good place to be, on a small warm world with air and water and gravity so gentle that you can stand up in it, in a room with a roof, in a bed, at the end of an ordinary day, with the floor holding you exactly as it always has and always will. Nothing near you is curved. Nothing near you is falling. Nothing is pulling at you except the same patient, faithful, unremarkable gravity that has held you every second of your life without once faltering, and which is holding you now quite gently in the warm. So let your breathing slow, and let the whole strange business drift away. Out past the roof and the clouds and the moon, out past the planets, out across 1,500 years of light, back to where it belongs, in the deep dark, minding its own business, and let the deep dark keep it. It has been keeping it very well for a very long time. It does not need watching, and it will not come any closer, and there is nothing about it that requires a single thought from you between now and the morning. Sleep now. You are not falling. You are held and safe and exactly where you should be, and the universe can look after its own strange corners tonight without any help from you.